At this very moment, you are hurtling through the universe at incredible speeds, yet your body notices absolutely nothing. Our planet rotates at nearly 1,000 miles per hour. At the same time, Earth circles the Sun at about 67,000 miles per hour. And beyond that, the entire solar system is streaking around the center of the Milky Way at more than 500,000 miles per hour. When you combine all of those layers of motion together, your quiet, everyday existence becomes one of the fastest journeys imaginable. Which raises an obvious question. If we're moving this quickly, why does it feel like we're perfectly still? And in a universe where every object is already in motion, what does speed actually mean? Tonight, we're pulling back the curtain on your true motion through the cosmos, and the numbers are far more extreme than most people ever realize. Let's begin with the motion closest to you, the rotation of Earth itself. Our planet spins continuously around its axis. This is measurable, observable, and completely understood. One full rotation takes 23 hours, 56 minutes, and 4 seconds, known as a sidereal day. It's slightly shorter than the 24-hour solar day we use on clocks because, while Earth is spinning, it's also traveling around the Sun, which changes the Sun's apparent position in the sky. Now stop and really picture what that means. The ground beneath you is turning through space like a gigantic spinning sphere. Every city, every ocean, every mountain, every person, all rotating together around Earth's center. Right now, your body is moving in a giant circle around the planet's axis. If you were standing directly on the equator, your rotational speed would reach roughly 1,040 miles per hour. That is faster than the speed of sound at sea level. While you sit there reading this, you are technically moving faster than a supersonic jet. Most people live farther from the equator, so the speed changes depending on latitude. In places like New York, the rotational velocity is closer to 800 miles per hour. In London, it drops to around 650. Near the poles, the movement becomes much smaller because you're rotating almost directly around the axis itself. So why can't you sense any of this? Because your surroundings are traveling with you. The atmosphere moves with Earth. Buildings move with Earth. Oceans move with Earth. Every object around you shares the same constant motion. Your senses detect differences in movement, acceleration, vibration, sudden changes, not steady velocity shared equally by everything nearby. This idea sits at the heart of relativity. Galileo described it centuries ago. Inside a smoothly moving system, constant motion becomes impossible to notice because there is no internal reference point telling you that you're moving at all. And Earth's rotation is only the first layer. Now let's zoom outward to Earth's path around the Sun. Our planet orbits the Sun from an average distance of about 93 million miles, a measurement astronomers call 1 astronomical unit. The orbit is almost circular, though technically it forms a slight ellipse. To complete one full revolution every year, Earth travels around 584 million miles through space. Break down that distance over the course of a year, and the numbers become staggering. Earth covers roughly 1.6 million miles every single day. Divide that further, and the result is around 66,600 miles per hour. Think about how absurd that really is. The legendary State Route 71, Blackbird, one of the fastest aircraft ever built, could reach just over 2,000 miles per hour. Earth is moving more than 30 times faster than that right now. And unlike a jet or rocket, Earth is an enormous world, weighing sextillions of tons, carrying oceans, continents, cities, and billions of people, while racing through empty space at unimaginable speed. Every second, our planet advances about 18.5 miles along its orbit. In the time it takes you to blink, Earth has already traveled dozens of miles through the solar system. By the time you finish reading this section, you will have moved thousands of miles through space without ever noticing. And once again, the reason you feel nothing is because the entire system moves together. You, the atmosphere, the ground, and everything around you are all orbiting the Sun as one connected structure. There's no roaring wind from Earth's motion because the air shares the same velocity as the planet beneath it. Inside a sealed environment, moving smoothly at constant speed, there is no simple experiment that reveals the motion. Water behaves normally. Objects fall normally. Life appears completely still. Yet outside that invisible frame of reference, you are flying through the universe at extraordinary speed. So now we have three layers. Earth spinning. Earth orbiting the sun orbiting the galaxy. If you're standing on the equator at local noon, you're moving at approximately 1,040 miles per hour from rotation. Earth is moving at approximately 66,600 miles per hour in its orbit. The sun is moving at approximately 490,000 miles per hour through the galaxy. If all these motions were aligned, you'd be approaching 1 million miles per hour. But they're not aligned. They're in different directions. The rotation is perpendicular to the orbital plane. The sun's galactic orbit is at an angle to the solar system's plane. The math becomes complicated, but the essential point is clear. You're moving at hundreds of thousands of miles per hour through space. You're traveling faster than any human has ever traveled. You're doing it right now. You're doing it continuously. And you feel absolutely still. Now we reach the layer that gets philosophical. The Milky Way galaxy itself is moving through space. Not stationary, not anchored, the galaxy is moving, carried along by invisible cosmic currents. When scientists ask how fast the galaxy is moving, they immediately face a problem. Moving relative to what? There's no fixed point in the universe. There's no cosmic landmark sitting absolutely still. Everything is moving. To measure the galaxy's motion, physicists needed to choose a reference frame. The reference frame they selected is the cosmic microwave background, or CMB. The cosmic microwave background is the oldest light in the universe. It's a faint glow of radiation left over from the Big Bang itself. It was emitted approximately 380,000 years after the Big Bang, when the universe had cooled enough for atoms to form and light to travel freely for the first time. The CMB fills the entire universe. You can't see it with your naked eyes, but it's all around you. It permeates everything. It's one of the most studied phenomena in all of science. The CMB is almost perfectly uniform in all directions. Almost. There's a very slight variation in temperature when you look in different directions. The variation is tiny. On one side of the sky, it's slightly warmer, about 3.3 millikelvin warmer. On the opposite side, it's slightly cooler. This tiny temperature difference is called a dipole anisotropy. It tells us something profound. This temperature difference exists because we're moving relative to the CMB. The direction that appears warmer is the direction we're moving toward. Light coming from that direction is blue shifted. The wavelengths are compressed because we're moving into the light, which makes it appear warmer. The direction that appears cooler is the direction we're moving away from. Light from that direction is red shifted. The wavelengths are stretched because we're moving away from it, making it appear cooler. By measuring this temperature difference, scientists can calculate how fast we're moving. The answer is approximately 1,342,000 miles per hour. 1,342,000 miles per hour. You're moving at over 1,000,000 miles per hour. Not because you're in a spaceship, not because you're in a rocket, not because you volunteered for any cosmic journey. You're moving at over 1,000,000 miles per hour because you're standing on a planet inside a solar system inside a galaxy that's moving through space at this incomprehensible velocity. Every second, the Milky Way moves approximately 373 miles relative to the CMB. Every minute, over 22,000 miles. Every hour, over 1.3 million miles. In the time it takes you to sleep for 8 hours, the Milky Way has carried you more than 10.7 million miles through space. You slept through a journey of over 10 million miles. But the Milky Way's motion isn't random. The galaxy is being pulled. Specifically, it's being pulled towards something called the Great Attractor. The Great Attractor is a gravitational anomaly located approximately 150 million light-years away in the direction of the constellations Hydra and Centaurus. It's not a single object, it's not a black hole or a star or a planet, it's a massive concentration of matter, possibly a supercluster of galaxies. Whatever it is, it's exerting gravitational influence on our galaxy and thousands of other galaxies in this region of space. The Milky Way is being pulled toward the Great Attractor. The word pulled is accurate here. Gravity is a fundamentally attractive force. Things fall toward massive objects. We usually think of falling as moving downward, but that's only because we're on a planet. In space, falling is the fundamental mechanism of motion. When you orbit something, you're falling toward it, but you're moving sideways fast enough to keep missing it. The Milky Way is falling toward the Great Attractor at hundreds of miles per second. But even the Great Attractor isn't the final layer. Beyond the Great Attractor is an even larger structure called the Shapley supercluster. It's located approximately 400 million light-years away. The Shapley supercluster is pulling on the Great Attractor, which is pulling on us. And beyond that are even larger cosmic filaments. The universe is structured like a vast web. Galaxies are arranged along enormous walls of gravity, stretching for hundreds of millions of light-years. These structures are all moving relative to each other. When you try to calculate your true speed through space, you face a problem. All these motions are happening simultaneously, they're happening in different directions. Earth is spinning on an axis that's tilted relative to its orbital plane around the Sun. The orbital plane is tilted relative to the galactic plane. The galaxy's motion relative to the CMB is in yet another direction. These motions aren't simple numbers that you can just add together. They're vectors. They have direction and magnitude. To find your true velocity, you'd need to use vector addition. You'd need to treat each motion as an arrow pointing in a specific direction. Then you'd combine them geometrically. The mathematics gets complicated. But here's what we know. You're moving at speeds well over 1 million miles per hour. The exact speed depends on where you are on Earth and what time of day it is. But regardless of the specifics, the conclusion is identical. You're moving faster than anything humans have created. You're moving at speeds that should be impossible to survive. You're moving at speeds that should be generating incredible forces that would crush your body. And yet, you feel still. Why? Why can't you feel any of this? The answer comes down to several key principles of physics. All of them combine to create a perfect illusion of stillness. First, constant velocity motion is undetectable. If you're moving in a straight line at a constant speed, there's no way to feel that motion. This is one of the foundational insights of physics. Special relativity, Einstein's theory about motion and space and time, begins with this principle. If you're moving at constant velocity, there's no experiment you can perform to detect that motion. You can only detect acceleration. Acceleration is a change in velocity, a change in speed, or a change in direction. When Earth orbits the Sun, it's constantly changing direction, so technically it's constantly accelerating. But the curve of the orbit is so gentle, so enormous, that the acceleration is imperceptible. It's so small that your body can't register it. Second, when everything around you is moving at the same speed, relative motion between you and your surroundings is zero. This is why you can't feel Earth's rotation. The air is rotating with you. The buildings are rotating. The furniture is rotating. Your body is rotating. Nothing is moving relative to anything else. Your sensory organs can only detect relative motion. They measure the difference between your motion and the motion of your surroundings. When there's no difference, they register nothing. Third, the accelerations involved are incomprehensibly small. Earth's centripetal acceleration due to rotation is approximately 0.034 meters per second squared at the equator. Compare that to gravitational acceleration, which is 9.8 meters per second squared. You're experiencing gravitational acceleration that's nearly 300 times stronger than the acceleration from Earth's rotation. Gravity completely overwhelms every other acceleration. The acceleration from Earth's orbit around the Sun is approximately 0.006 meters per second squared. That's over 1,600 times weaker than gravity. The acceleration from the Sun's orbit around the galaxy is so small, it's essentially zero. All of this cosmic motion generates accelerations far too tiny for human perception. Your body is completely insensitive to them. The only accelerations you can feel are the ones comparable to gravity. When a car accelerates, you feel pushed backward into your seat. That's an acceleration of maybe 2 or 3 meters per second squared. It's strong enough to compete with gravity. That's why you feel it. When an elevator starts moving, you feel lighter or heavier. That's because the elevator's acceleration is adding to or subtracting from gravity. But the motion of Earth through space is perfectly smooth, perfectly constant, perfectly undetectable to human biology. There's one more reason we can't feel any of this motion. It's about the environment we're moving through. When you drive a car through air, you feel wind. The air is stationary relative to the Earth, so as you move through it, you collide with air molecules. This collision creates a force that you can feel. The faster you go, the more dramatic this force becomes. At high speeds, wind resistance becomes a major problem. But when Earth moves through space, it's moving through something very different. Space isn't completely empty. There are particles, there's gas, there's dust, there's cosmic radiation. But the density is so incredibly low that it's almost not there. At the speeds Earth is moving, even the thin gas between stars doesn't create any noticeable drag. There's no cosmic wind pushing against Earth. There's no resistance slowing us down. There's nothing creating a sensation of motion. We're moving through a void. And a void doesn't push back. It doesn't resist. It doesn't create sensation. We're racing through space at over 1 million miles per hour, and the void offers no resistance whatsoever. Now let's talk about something strange, something that challenges our understanding of motion itself. The universe is expanding. For almost a century, scientists assumed the universe was either static or contracting. The prevailing wisdom was that the Big Bang scattered all matter outward, but gravity should be pulling everything back together. The expansion should be slowing down. Gravity always attracts. Matter pulls on matter, so the expansion should decelerate. It was a logical conclusion based on how gravity works. In the late 1990s, astronomers set out to measure how much the expansion was slowing. They studied Type Ia supernovas, exploding stars visible across billions of light years. These supernovas are useful because they all have roughly the same brightness. If you see a supernova that's dimmer than expected, you know it's farther away. By measuring brightness and redshift, you can determine both distance and recession velocity. This would show how the expansion rate has changed over time. The astronomers expected to find deceleration. They expected the expansion to be slowing down. What they found instead shocked them. The expansion is accelerating. Distant supernovas were dimmer than expected. They were farther away than they should have been. The universe had expanded more than predicted. The expansion rate was increasing, not decreasing. This was a complete inversion of expectations. It contradicted decades of assumptions. Both teams of astronomers, working independently, double-checked their results. They looked for errors in methodology. They considered alternative explanations. But the data was unmistakable. The expansion of the universe is speeding up. In 2011, the 3 lead scientists on this discovery, Saul Perlmutter, Brian Schmidt, and Adam Rees, were awarded the Nobel Prize in Physics. But the discovery created a fundamental question. You'd also experience length contraction. At high speeds, distances in the direction of travel appear shorter. At 99% of light speed, the 4.24 light-year distance to Proxima Centauri would appear to be only about 0.6 light-years from the spacecraft's perspective. This isn't an optical illusion. It's a real physical effect. Space itself is contracted in the direction of motion. From Earth's perspective, a journey at 99% of light speed takes 4.3 years. From the spacecraft's perspective, the journey takes about 7 months. Both perspectives are correct. Both are valid descriptions of the same event. It's a consequence of traveling near light speed. Time dilation and length contraction are as real as gravity. Interstellar space is filled with motion. Every star has its own velocity. Every object has its own trajectory. Navigating through it requires understanding not just your motion, but the motion of every object you want to reach. It requires precise measurements of stellar positions and velocities. It requires powerful computers calculating trajectories years in advance. It requires technology we don't yet possess. But in principle, it's possible. The laws of physics allow it. Now let's talk about some practical consequences of all this cosmic motion. First, there's a phenomenon called stellar aberration. Because we're moving through space, the direction we see starlight coming from is slightly different from the star's true direction. This was first observed by James Bradley in 1728. Bradley was trying to measure stellar parallax. The apparent shift in a star's position due to Earth's motion around the Sun parallax is a geometric effect. As Earth orbits the Sun, our viewing angle to nearby stars changes. The stars appear to shift against the background of more distant stars. But Bradley found something different. He found stellar aberration. The apparent position of a star shifts throughout the year due to Earth's changing velocity. When Earth is moving toward a star, the star appears slightly ahead of its true position. When Earth is moving away, the star appears behind. The effect is similar to how rain appears to come at an angle when you're driving. If rain is falling straight down and you're stationary, it hits you from above. But if you're moving forward, the rain appears to come from ahead of you. You tilt your umbrella forward. The faster you move, the more you tilt the umbrella. The same thing happens with starlight. Stars appear to shift position because we're moving into the light. Bradley measured the aberration angle to be about 20.5 arcseconds. That's less than 0.006 degrees. Tiny, but measurable. From the aberration angle and Earth's orbital speed, Bradley calculated the speed of light. His result was remarkably accurate. The aberration angle depends on the ratio of Earth's orbital speed to light speed. Earth orbits at about 1812 meters per second. Light travels at about 186,000 meters per second. The ratio is about 1 to 10,000. The aberration angle equals Earth's speed divided by light speed, about 20 arcseconds. Exactly what Bradley observed. Stellar aberration was one of the first direct proofs that Earth moves. Before Bradley's discovery, the heliocentric model was still debated. Some scientists believed the Sun orbited Earth. Bradley's observation of stellar aberration provided direct evidence that Earth must be moving. There was no other way to explain it. If Earth were stationary, stars would appear in fixed positions throughout the year. But they don't. Their positions shift in a pattern that exactly matches Earth's orbital motion. Stellar aberration affects every star in the sky. The exact amount and direction of shift depends on the star's position and Earth's current velocity. Modern telescopes must correct for aberration to measure stellar positions accurately. The Hubble Space Telescope accounts for it. The Gaia spacecraft, a European Space Agency mission mapping over 1 billion stars, must correct for aberration at incredible precision. Gaia measures stellar positions down to micro-arcseconds, which is a millionth of an arcsecond. At that precision, Gaia must account not just for Earth's orbital motion, but for the Sun's motion through the galaxy. The Sun is moving at about 155 meters per second relative to nearby stars. That's about 560,000 miles per hour. This creates an aberration effect, about twice as large as the one from Earth's orbit. Gaia must correct for this to get accurate positions. By measuring and correcting for aberration, Gaia determines the true positions of stars. By tracking how those positions change over time, Gaia determines stellar velocities through the galaxy. This is creating the most detailed map ever made of the Milky Way's structure and motion. We're learning how the galaxy rotates, we're learning how stars move through it, we're learning how spiral arms form and dissolve over time. All because we can measure aberration with incredible precision. Aberration is direct evidence that we're moving through space. Second, there's the effect on cosmic radiation. Earth is constantly being hit by high-energy particles from space. Cosmic rays are mostly protons traveling at close to the speed of light. Some travel at 99.99% of light speed. They come from supernova explosions. They come from neutron stars. They come from black holes. They come from other violent events in the galaxy and beyond. When cosmic rays hit Earth's atmosphere, they create showers of secondary particles. A single high-energy cosmic ray can create thousands or millions of secondary particles. These particles rain down on the surface constantly. About 10,000 cosmic ray particles hit every square meter of Earth's surface every minute. You're being hit by cosmic rays right now. Dozens are passing through your body every second. Most pass through harmlessly. Your body is mostly empty space at the atomic level. Cosmic rays usually pass straight through, but some can damage DNA and potentially cause cancer. You have two forms of protection. Earth's magnetic field deflects many cosmic rays. Charged particles spiral along magnetic field lines. This is why the aurora borealis and aurora australis occur near the poles. Those lights are caused by cosmic rays hitting the upper atmosphere. Second, the atmosphere itself absorbs cosmic rays. At sea level, there's about 10 tons of air above every square meter. Cosmic rays collide with air molecules. The collisions create showers of particles that lose energy as they cascade down through the atmosphere. By the time they reach the ground, most energy has been absorbed. But if you fly in an airplane, you're exposed to higher cosmic radiation. At cruising altitude of 35,000 feet, there's only about 3 tons of air above you. Cosmic radiation at that altitude is about 100 times higher than at sea level. Pilots and flight attendants receive measurable radiation doses over their careers. Astronauts in space face much higher levels. The International Space Station orbits at about 250 miles up. The atmosphere is essentially absent. The magnetic field is weaker. Astronauts receive radiation doses about 150 times higher than people on the ground. During a 6-month stay on the ISS, an astronaut receives about the same radiation dose as a full-body CT scan every 5 or 6 days. Mars is worse. Mars has no global magnetic field. It has almost no atmosphere. The atmospheric pressure is less than 1% of Earth's. Astronauts on Mars would face the full force of cosmic radiation. A trip to Mars takes 6 to 9 months each way. Astronauts would be traveling through interplanetary space with essentially no protection except their spacecraft's hull. The radiation dose would be significant enough to increase cancer risk. If we ever send humans beyond Mars, the problem becomes even worse. We'd need to shield spacecraft with water or plastic, materials with lots of hydrogen atoms that stop cosmic rays. We could use magnetic fields to deflect particles. We could create artificial magnetospheres around spacecraft. We could limit mission duration. But cosmic radiation is a fundamental challenge of space travel. It's a consequence of moving through the galaxy at hundreds of thousands of miles per hour. We're constantly plowing through high-energy particles. There's no way to completely avoid them. Third, there's the cosmic microwave background. Because we're moving relative to the CMB at over 1,000,000 miles per hour, the CMB appears slightly warmer in the direction we're moving and slightly cooler in the direction we're moving away from. This dipole anisotropy is how we measure our motion through space, but it also means the universe looks slightly different depending on which direction you're looking. When scientists study the CMB to understand the early universe, they must correct for our motion. They must subtract the dipole anisotropy to see the underlying structure. This anisotropy is crucial for cosmology. It's how we know the universe isn't completely uniform. It's how we know our motion through it. Without the ability to measure this motion, we'd understand far less about the cosmos. Now let's consider what this cosmic motion means for the future. Earth's rotation is gradually slowing down. The moon creates tidal bulges on Earth. The moon's gravity pulls on Earth more strongly on the side facing the moon and less strongly on the far side. This difference in gravitational pull stretches Earth. The oceans deform significantly. Water bulges toward the moon, creating high tide. Water on the far side also bulges. As Earth rotates, different parts pass through these bulges, creating the tidal cycle most of us experience. But Earth's rotation is faster than the moon's orbit. Earth rotates once every 24 hours. The moon orbits once every 27.3 days. Earth is trying to drag the tidal bulges along as it rotates, but the moon's gravity pulls them back. The bulges lag slightly behind Earth's rotation. This creates friction. The friction dissipates energy. That energy comes from Earth's rotation. As Earth loses rotational energy, it spins more slowly. The effect is small. Earth's day is getting longer by about 1.7 milliseconds per century, 1.7 thousandths of a second every 100 years. You'd never notice it, but over millions of years it accumulates. About 600 million years ago, a day on Earth was only about 21.5 hours. When the first complex multicellular life was evolving in the oceans, Earth was spinning faster. A year still had about 365 days, but each day was shorter, so there were more days in a year. We know this from ancient corals. Corals lay down daily growth rings like trees. By counting rings between seasonal markers, paleontologists can determine how many days were in a year hundreds of millions of years ago. Going back further, when the moon first formed about 4.5 billion years ago, Earth was spinning much faster. A day might have been only 4 or 5 hours. The moon was much closer, only about 15,000 miles away instead of 239,000. From Earth's surface, the moon would have appeared enormous, about 15 times larger than now. Tides would have been massive, hundreds of feet high. Over billions of years, two things happened. Earth's rotation slowed. The moon drifted farther away. These are connected. As Earth's rotation slows, Earth loses angular momentum. But angular momentum is conserved. The momentum is transferred to the moon. The moon gains angular momentum, which causes its orbit to expand. The moon is currently drifting away at about 1.5 inches per year. We know this precisely because Apollo astronauts left retroreflectors on the moon. Scientists shine lasers at these reflectors and measure how long the light takes to bounce back. Tracking this over decades shows the moon is receding at about 1.5 inches yearly. In the future, Earth's rotation will continue slowing, and the moon will continue drifting away. Eventually, billions of years from now, Earth's rotation will slow until one side always faces the moon. This is called tidal locking. At that point, a day on Earth will equal the moon's orbital period, about 47 current days. One side will always see the moon hanging motionless in the sky. The other side will never see it. This has already happened to the moon. The moon is tidally locked to Earth. It rotates once per orbit. That's why we always see the same face. The far side is never visible from Earth. Eventually, the same thing will happen to Earth, but this will take billions of years. By then, the sun will likely have destroyed or rendered Earth uninhabitable. Earth's orbit around the sun is also changing. The sun is losing mass through solar wind. Every second, the sun converts about 4 million tons of mass into energy through fusion. That mass is lost. As the sun loses mass, its gravitational pull weakens. Earth's orbit gradually spirals outward. The effect is tiny, only about 1.5 centimeters per year. Less than an inch, but over billions of years it adds up. Eventually, Earth might drift far enough to survive when the Sun becomes a red giant. The Sun will expand to about 250 times its current size. Currently, that would reach past Earth's orbit. But if Earth has drifted far enough, it might avoid being swallowed. It will still be scorched. The oceans will boil. The atmosphere will be stripped. But the planet might survive as a barren rock. The Sun will complete many more orbits around the galactic center over the next few billion years. Each orbit takes about 230 million years. In another 4 billion years, the Sun will have completed about 17 more orbits. But this cosmic dance will be interrupted. The Milky Way will collide with Andromeda. Andromeda is the nearest large galaxy to us. It's about 2.5 million light-years away, about 15 quintillion miles. Andromeda is moving toward us at about 68 meters per second, about 244,800 miles per hour. Andromeda is on a collision course with the Milky Way. In about 4 billion years, Andromeda and the Milky Way will collide. 4 billion years sounds impossibly distant. 4 billion years ago, Earth had just cooled enough to have liquid water. Life was just beginning. Multicellular life wouldn't emerge for another 3 billion years. Humans have existed for only about 300,000 years. 4 billion years is over 13,000 times longer than all of human history. But the collision will happen. The evidence is clear. Andromeda's blue shift shows it's approaching. Measurements show it's not going to miss us. The trajectory calculations confirm a collision. Actually, there might be a near miss on the first pass. The galaxies might swing past each other, gravitationally distorting each other. Then they'd swing back for a second collision. Eventually, they'd merge completely. Computer simulations have modeled this. The animations are stunning. Two spiral galaxies approach each other. Their spiral arms distort. Tidal forces pull and stretch the galaxies. Long streamers of stars get pulled into space. The galaxies pass through each other. But here's the important part. Stars are so far apart that they almost never collide. The Milky Way has about 200 billion stars. Andromeda has about 1 trillion. But galaxies are mostly empty space. The average distance between stars in our region is about 4 light-years. That's about 25 trillion miles. A star is typically about 1 million miles across. That's a million-mile object in a region 25 trillion miles across. It's like having a grape in a space the size of North America. When galaxies collide, stars mostly pass by each other harmlessly. The probability of any two stars actually colliding is essentially zero. If the Sun and Earth still exist in 4 billion years, they'll probably survive unscathed. But the night sky will look completely different. As Andromeda approaches, it will grow larger in the sky. Currently, it appears about 6 times wider than the Moon, but it's faint. As it gets closer, it will get brighter and larger. Eventually, it will dominate the sky. A massive glowing band stretching across half the visible sky. During the collision, new stars will form at incredible rates. Gas clouds from the two galaxies will collide. Unlike stars, gas doesn't pass through gas. When clouds collide, they compress. Compressed gas can collapse under its own gravity and form new stars. Millions of new stars will be born. The night sky will be filled with bright young stars and glowing gas clouds. It will be spectacular. The collision will disrupt the galaxies, structures. Spiral arms will be torn apart. Stars will be flung into intergalactic space. The Sun might be one of them. Computer simulations suggest 10 to 20% of stars will be ejected. If the Sun is ejected, it will end up in intergalactic space. The night sky would go dark. No Milky Way. No Andromeda. Just the Sun, planets, and empty black sky. The nearest stars would be millions of light-years away. Invisible to the naked eye. It would be lonely. Or the Sun might stay within the merged galaxy. Either way, the merger will produce something new. The two spiral galaxies, will merge into a single large elliptical galaxy. Elliptical galaxies are blob-shaped, without spiral arms. They contain mostly old stars. Star formation has largely stopped. Astronomers have already named this future galaxy Milky, a combination of Milky Way and Andromeda. Milky will contain about 1.2 trillion stars. It will be much larger than either galaxy alone. It will continue moving through space, pulled by gravity toward distant structures. Finally, let's talk about the expansion of the universe and what it means for the far future. The expansion is accelerating. Dark energy is pushing space apart. It comprises about 68% of the universe's total energy. As space expands, more space is created. More space means more dark energy. The acceleration compounds. In the far distant future, billions of years from now, the acceleration will carry distant galaxies beyond our cosmic horizon. Their light will never reach us. The observable universe will shrink, not because the universe is getting smaller, but because we're being cut off from distant parts of it. Eventually, only the galaxies gravitationally bound to our local group will be visible. The local group contains the Milky Way, Andromeda after the merger, and a few dozen smaller galaxies. Everything else will have been carried away. An observer in the far future will look up and see only their own galaxy, and maybe a few nearby ones. They won't see any other galaxies. They won't see the cosmic microwave background. It will be redshifted into invisibility, its wavelength stretched to infinity. They'll have no evidence the universe is expanding. They'll think their galaxy is the entire universe. They'll have no way to discover the Big Bang. We're living in a special cosmic era, an era when the universe is old enough for stars and galaxies and intelligent life to have formed, but young enough that we can still see the evidence of the Big Bang. We can still see distant galaxies. We can still measure the expansion. We can still detect the cosmic microwave background. In the far future, that won't be possible. The evidence will have disappeared. This makes our moment unique, not just in human history, but in cosmic history. We exist in a window of time when the universe's deepest secrets are still visible to us. So what does all this motion mean? What does it mean that you're racing through space at terrifying speeds? The answer lies in how we understand our place in the universe. For most of human history, we thought we were at the center of everything. The Earth was still. Everything else moved around us. The sun orbited us. The stars orbited us. We were special, important, the point around which the cosmos revolved. Then Copernicus showed that Earth orbits the sun. The Church opposed this idea for centuries, but evidence accumulated. We discovered the sun is just one star among billions in the Milky Way. We're not at the center of the galaxy. We're located in the suburbs, halfway between the center and the edge. Nothing special about our location. We discovered the Milky Way is just one galaxy among trillions in the universe. We're not at the center of the universe. Actually, the universe doesn't have a center. The Big Bang happened everywhere at once. Every point in space is equally valid as a center. And now we know we're moving through space at over 1 million miles per hour, being pulled by gravity toward distant structures we can barely see. We're not at the center of anything. We're not stationary. We're just one small planet in one small solar system in one galaxy among trillions. This is sometimes called the Copernican principle, the idea that we're not special. There's nothing unique about our location or our motion. We're typical, average, unremarkable. In one sense, that's humbling. It puts us in perspective. It reminds us that the universe doesn't revolve around us. We're not the main characters in some cosmic drama. We're observers trying to understand. But there's another way to look at it. We're small, yes. We're moving at incredible speeds, yes. We're not at the center of anything, yes. But we're the only beings we know of who can understand this. We're the only ones who can measure the cosmic microwave background and calculate our motion. We're the only ones who can build telescopes and see galaxies billions of light years away. We're the only ones who can figure out we're moving at over 1 million miles per hour and explain why we can't feel it. We're the only ones who can contemplate our place in the cosmos. That's extraordinary. Out of all the planets in all the galaxies, Earth produced a species capable of understanding the universe. We can ask questions, we can figure out answers, we can think, we can wonder. We're made of atoms forged in the hearts of ancient stars. We're the universe's way of knowing itself. Through us, unconscious matter has become conscious. We're racing through space at terrifying speeds. We're hurtling through a void at velocities that should be incomprehensible. But we're awake. We're aware. We're conscious. And that makes us special in a different way. Not special because of where we are. Not special because we're still. Special because of what we can do. We can think. We can question. We can explore. We can understand. The next time you feel still, remember this. You're not still. You're moving at speeds that would be impossible to survive in any vehicle humans have built. You're moving at speeds that exceed the fastest jets, the fastest rockets, the fastest anything we've ever created. You're racing through the cosmic void at over 1,000,000 miles per hour. But you feel still because you're part of a reference frame moving together. You and Earth and the solar system and the galaxy and everything around you are moving in concert. There's nothing to feel, no relative motion, no sensation, yet you exist in this moment. You exist in this cosmic era when the universe is still young enough to see its own history. You exist in an age when you can know these things, when you can understand. In 4 billion years, when Andromeda crashes into the Milky Way, when the night sky is filled with new stars, when the geometry of the local universe is forever changed, no observer will remember this moment. No one will know that we once could see so far, that we once could measure the expansion of space itself. But right now, in this moment, you can know these things. You can understand your motion. You can comprehend that you're racing through space at terrifying speeds, carried along on a journey that began billions of years ago and will continue long after you're gone. You're part of something vast, something dynamic, something in constant motion. And even though you can't feel it, even though it seems like you're sitting still, you're on the ride of a lifetime. You're racing through space, right now, every moment, at over 1,000,000 miles per hour. The Earth is racing through space at terrifying speeds. And so are you. Close your eyes for a second and just listen. Feel the floor beneath your feet, the chair holding your weight, the absolute stillness of the room around you. It feels safe. It feels permanent. But that serenity is a lie manufactured by your human biology. Right now, you are strapped to a cosmic projectile hurtling through a dark, frictionless void at speeds that defy human comprehension. If the universe suddenly slammed on the brakes, everything you have ever known would be instantly pulverized into subatomic dust. We like to think of our planet as a stable home, but in reality, the Earth is racing through space at terrifying speeds, dragging us along on a multi-layered journey toward an unknown destination. Let's start with the most intimate layer of this hidden motion, the one happening right beneath your feet. The planet is spinning. To us, a day is just a gentle cycle of light and shadow, but mathematically, it is a high-speed sprint. The Earth rotates on its axis once every 23 hours, 56 minutes, and 4 seconds. If you happen to be standing at the equator, the widest part of our planetary carousel, you are being whipped around at roughly 1,040 miles per hour. That is faster than the speed of sound. Imagine a jet fighter screaming through the sky, breaking the sound barrier with a deafening boom. You are traveling faster than that jet right this second, yet there is no roar of engines, no wind tearing at your face, and no sensation of motion. As you move away from the equator, the physical circle you travel gets smaller, so the speed drops. In New York, you are rotating at about 794 miles per hour. In London, it is around 650 miles per hour. Even at the poles, where you are essentially spinning in place like a slow-turning coin, you are still trapped on a moving stage. We do not fly off into the atmosphere because gravity glues us down, and we do not feel the wind because the entire atmosphere is pinned to the planet, rotating right along with us. There is no friction, no drag, and no relative movement between you and the room around you. Your senses are completely blind to it, but that 1,000-mile-an-hour spin is nothing but a crawling pace compared to the second layer of our journey. While the Earth is spinning like a top, it is also falling around the Sun. We are locked in an orbital dance, tracing an enormous, slightly oval path through space at an average distance of 93 million miles. The Earth travels along its orbit at approximately 66,600 miles per hour. Let that number sink in. The fastest manned aircraft in human history, the legendary State Route 71 Blackbird, could barely scratch over 2,000 miles per hour. The planet you are sitting on right now is moving 30 times faster than a speeding spy plane. Every single second that ticks by, you advance 18.5 miles through the solar system. In the time it takes you to draw a single breath, you have traveled further than the length of Manhattan. We are a massive ball of rock and iron, weighing sextillions of tons, bulleting through space. The reason our oceans do not spill into the void and our buildings do not collapse from the sheer momentum is the fundamental principle of relativity. Because our speed is almost perfectly constant, and because everything in our planetary reference frame is moving in perfect unison, the physics inside our earthly room remains completely undisturbed. You only feel acceleration, a change in speed or direction. The curve of Earth's orbit is so vast, and the speed so steady, that the actual acceleration is completely drowned out by the everyday pull of gravity. If you think 66,000 miles per hour is terrifying, what causes the acceleration? Gravity pulls things together. It slows down expansion. It cannot speed up expansion. Something else must be pushing space apart, something we don't understand. Scientists call it dark energy. The name is intentionally vague. It's a placeholder. It doesn't explain what dark energy is. It just acknowledges that something is causing the acceleration and we're ignorant about its nature. The leading hypothesis is that dark energy is a property of space itself. Space isn't empty. Even vacuum contains energy. This is called vacuum energy. In quantum field theory, the vacuum is filled with quantum fluctuations. Virtual particles constantly pop in and out of existence. These fluctuations have energy. If empty space has energy, and the universe is expanding, then as the universe gets larger, the amount of space increases. More space means more vacuum energy. This additional energy pushes space apart. The more the universe expands, the more vacuum energy accumulates. The expansion accelerates. It's a self-reinforcing cycle. Dark energy comprises approximately 68% of the total energy content of the universe. 75% actually is dark matter, something equally mysterious. Only 5% of the universe is ordinary matter. Atoms, stars, planets, everything visible, everything we can see, everything we understand. Only 5%. The expansion of the universe is not motion through space. It's the expansion of space itself. It's fundamentally different from the other motions we've discussed. The expansion doesn't have a direction. It's happening everywhere simultaneously. Space between galaxies is expanding. Space between stars is expanding. Space within galaxies is expanding, though gravity holds the galaxies together and prevents them from being torn apart. Galaxies farther away from us are receding faster. This is described by Hubble's law. The recession velocity of a galaxy is proportional to its distance. The current value of the Hubble constant is approximately 46 meters per second per megaparsec. A megaparsec is approximately 3.26 million light-years. For every 3.26 million light-years of distance, the recession velocity increases by approximately 46 meters per second. A galaxy 100 million light-years away is receding at approximately 1,400 meters per second. That's over 5 million miles per hour. A galaxy 1 billion light-years away is receding at approximately 14,000 meters per second. That's over 50 million miles per hour. A galaxy 10 billion light-years away is receding at approximately 140,000 meters per second. That's over 500 million miles per hour. At a certain distance, the recession velocity exceeds the speed of light. This doesn't violate relativity. Nothing is moving faster than light through space, but space itself can expand faster than light. The boundary where recession velocity equals light speed is the edge of the observable universe. Beyond that edge, galaxies are receding so fast that their light will never reach us. They're beyond our cosmic horizon. We'll never see them. We can never know them. The observable universe has a radius of approximately 46.5 billion light-years. That's the distance to the farthest objects we can possibly observe. Anything beyond that is forever beyond our reach. So when you think about your motion through space, there are multiple layers. Most importantly, there's no single correct answer to the question, how fast am I moving? The answer depends entirely on what you're measuring your motion relative to. Relative to Earth, you're moving slowly. Maybe you're sitting still. Maybe you're walking at 3 miles per hour. Maybe you're driving at 60 miles per hour. Those are meaningful speeds in the context of Earth. Relative to Earth's center, you're moving up to 1,040 miles per hour from rotation. Relative to the Sun, you're moving at 66,600 miles per hour. Relative to the galactic center, you're moving at 490,000 miles per hour. Relative to the cosmic microwave background, you're moving at 1,342,000 miles per hour. Relative to distant galaxies, you're moving slower or faster, depending on which galaxies you choose and how the expansion of space is affecting their apparent motion. All of these answers are correct. They're just measuring different things. They're all valid ways of describing motion in different reference frames. This is the deepest insight physics has given us. Motion is relative. There's no absolute reference frame. There's no cosmic grid determining who's moving and who's standing still. Everything is moving relative to something else. When you say you're sitting still, you mean you're still relative to the ground. But the ground is moving relative to Earth's center. Earth's center is moving relative to the Sun. The Sun is moving relative to the galactic center. The galaxy is moving relative to the CMB. The CMB itself is just a reference frame we've chosen because it's useful. It's not more fundamental than any other reference frame. In a deep sense, absolute motion doesn't exist. Only relative motion exists. Now let's consider the implications for space exploration. If we're moving this fast, shouldn't we be able to take advantage of it? Shouldn't we be able to jump off Earth and be carried to other planets by all this motion? The answer is no. Here's why. When you jump off Earth, you're still moving with Earth. You're still orbiting the Sun at 66,000 miles per hour. You're still moving with the solar system at 490,000 miles per hour. You inherited all of Earth's motion. You didn't escape it. You can't escape it by jumping. Gravity is keeping you attached to Earth's motion. You're locked in. To travel to another planet, you don't need to overcome Earth's absolute motion through space. You only need to change the relative motion between Earth and your destination. Mars orbits the Sun at about 54,000 miles per hour. Earth orbits at about 66,600 miles per hour. When we send a spacecraft to Mars, we're not fighting against Earth's motion through the solar system. We're just adjusting the spacecraft's orbit so it intersects with Mars's orbit. The spacecraft leaves Earth already moving at 66,600 miles per hour around the Sun. It doesn't start from zero velocity. It's already in the solar system's reference frame. All the rocket needs to do is change the orbit slightly. Speed up a bit to move into a higher, slower orbit that reaches out to Mars's distance. Then slow down when arriving at Mars to match Mars's orbital speed. The fact that the Sun is moving through the galaxy at hundreds of thousands of miles per hour is completely irrelevant. Mars is moving at the same speed. They're in the same reference frame. Both planets are being carried along by the Sun at the same velocity. This is why spacecraft navigation is planned using the solar system as the reference frame. The Sun is essentially stationary from this perspective. The planets orbit around it. That's all we need to know. We don't care about the galaxy's motion. We don't care about cosmic motion. Within the solar system, the Sun is effectively still. Navigation in space is entirely about reference frames. When you're on Earth looking at Mars, you see it moving across the sky. But this motion is complicated. Part of it is Mars's actual orbit. Part of it is Earth's orbit. As Earth moves, our perspective changes. Mars appears to move relative to the background stars. Sometimes Mars appears to move backward in the sky. This is called retrograde motion. It happens when Earth, moving faster in its inner orbit, overtakes Mars in its slower outer orbit. From our perspective, Mars seems to reverse direction temporarily. Ancient astronomers were puzzled by this. They invented complicated systems of circles within circles to explain it. But once you understand that both planets are orbiting the Sun, retrograde motion is just a perspective effect. Simple geometry. When planning a Mars mission, engineers must predict where Mars will be months in advance. They must calculate a trajectory that intersects Mars's position at the exact moment the spacecraft arrives. They must account for gravitational influences from Earth, the Sun, Mars, and sometimes Jupiter. They must plan course corrections for the journey. The mathematics is extraordinarily complex, but it's all done within the solar system reference frame. The galaxy's motion is irrelevant. Imagine trying to navigate to another star. Suddenly the galaxy's motion matters. Other stars are moving at different speeds in different directions relative to the Sun. Each star has its own velocity vector. The nearest star to us is Proxima Centauri, approximately 4.24 light-years away. That's about 25 trillion miles. Proxima Centauri has a radial velocity of about 14 meters per second toward us. It also has proper motion of about 2.3 arcseconds. That's the motion across our line of sight. At Proxima Centauri's distance, this corresponds to about 12 meters per second across the sky. Combined, Proxima Centauri is moving at about 24 meters per second relative to the Sun. That's about 86,400 miles per hour. If we sent a spacecraft to Proxima Centauri, we'd need to account for that relative motion. We'd aim not at where Proxima Centauri is now, but where it will be when we arrive. At current spacecraft speeds, the journey would take tens of thousands of years. Voyager 1, the fastest human-made object to leave the solar system, is traveling at about 38,000 miles per hour relative to the Sun. At that speed, reaching Proxima Centauri would take over 73,000 years. In 73,000 years, Proxima Centauri would move significantly. The star travels about 24 miles every second. Over 73,000 years, that's approximately 55 billion miles. Proxima Centauri would be more than twice as far from its current position as it currently is from the Sun. You couldn't aim at where the star appears now. You'd have to aim at where it will be. You'd have to account for both the star's motion and the Sun's motion. The Sun is moving relative to nearby stars. From Proxima Centauri's perspective, the Sun is moving toward or away. It's a moving target while you're moving. It's like trying to hit something that's moving while you yourself are also moving. Not in a straight line, but in curves determined by the gravity of every object you pass. The mathematics becomes complicated. This is why interstellar navigation is so challenging. It's not just the distance. It's not just the incomprehensible emptiness of space. It's the fact that everything is moving. Every object in the galaxy is moving at its own velocity. Every star is moving. The spaces between stars are expanding. You can't just launch a spacecraft and aim at a target. The target is moving. You're moving. Everything is moving. We'd need to travel much faster for interstellar exploration to be practical. Breakthrough Starshot, a proposed mission, aims to send tiny light sail probes to Proxima Centauri at about 20% of the speed of light. That's approximately 134 million miles per hour. At that speed, the journey would take approximately 20 years from Earth's perspective. But we'd still need to account for Proxima Centauri's motion. The star would move about 10 billion miles during the 20-year journey. You'd need to aim that far ahead of where the star appears now. At 20% of light speed, relativistic effects become important. Time dilation becomes noticeable. Time on the probe would run about 2% slower than time on Earth. The journey would take 20 years from Earth's perspective, but about 19.6 years from the probe's perspective. The difference is small but measurable. If we ever figured out how to travel faster, relativistic effects would become more dramatic. At 50% of light speed, time dilation is about 13%. At 90%, it's over 50%. At 99%, time on the spacecraft runs 7 times slower than time on Earth. Every single day, the Earth's atmosphere slams into millions of tiny space rocks, dust particles, and debris left behind by comets. Because the Earth is traveling at 66,600 miles per hour around the Sun, these collisions do not happen gently. When a speck of space dust enters our upper atmosphere, it isn't just falling due to gravity. It is experiencing a head-on collision with a planetary windshield moving at hypervelocity. The friction between the meteoroid and the thin air molecules compresses the gas ahead of it so violently that the temperature skyrockets to thousands of degrees in a split second. This is what creates a shooting star. That brilliant, fleeting streak of light across the night sky is the physical manifestation of Earth's terrifying orbital speed. It is a visual warning of the kinetic energy inherent in our daily journey, a reminder that we are sitting inside a cosmic bumper car, tearing through a field of debris at speeds that vaporize rock instantly. Yet, as violent as those atmospheric shield impacts are, they are localized events within our solar system. The true frontier of our motion is found at the very edge of the Sun's domain, where the solar wind meets the interstellar medium. The Sun constantly exhales a stream of charged particles that blows outward like a protective balloon, creating a region called the heliosphere. As the solar system screams through the galaxy at nearly 500,000 miles per hour, this magnetic bubble plows through the thin gas and dust of interstellar space. It creates a cosmic wake, much like the bow wave of a ship cutting through the ocean. In the past, scientists believed this high-speed plunge created a massive, permanent shock wave ahead of us, a bow shock, where the interstellar gas is suddenly compressed, while newer data suggests the transition might be smoother than a full shock wave. The boundary is still a place of intense physical interaction, a cosmic frontline where our solar system violently asserts its presence against the rest of the Milky Way. We are actively carving a tunnel through the galaxy, leaving a long trail of solar particles in our wake as we barrel toward the stars. The mechanics of this galactic journey become even more dizzying when you realize that our solar system isn't even aligned with the flat plane of the galaxy. The Milky Way is a giant spinning disk of stars, but the plane of our solar system, the flat tabletop where the planets orbit the Sun, is tilted at an angle of about 60 degrees relative to the galactic disk. Furthermore, the Sun doesn't just fly in a flat circle around the center of the galaxy. It bobbles up and down like a cork floating in water. As we make our 230 million-year journey around the galactic core, the gravitational pull of the dense sheet of stars in the galactic plane pulls the Sun toward it. The Sun plunges through the plane, overshoots due to its immense momentum, slows down as the gravity of the disk pulls it back, and then plunges back through in the opposite direction. This vertical oscillation takes tens of millions of years to complete a single cycle. Right now, we are riding a planet that is spinning on a tilted axis, orbiting a star on a tilted plane, while that star corkscrews its way up and down through the crowded disk of a massive rotating galaxy. It is a roller coaster ride written in the language of orbital mechanics, operating on scales of time and space that reduce all of human history to a microscopic fraction of a single turn. When you stack all these layers together, you begin to see why the concept of a fixed point in space is completely meaningless. In our daily lives, we rely entirely on fixed points. We reference our location by a street corner, a mountain range, or a coordinate grid on a map. But if you were to teleport off the surface of the Earth and leave yourself floating in the exact spatial coordinates you occupied just 5 minutes ago, you would instantly find yourself stranded in the deep vacuum of space, thousands of miles away from the planet. The Earth would have spun out from beneath you, surged ahead in its orbit around the Sun, and been dragged into a new sector of the galaxy by the Sun's relentless flight. Space has no memory of where we were. It is a vast, unmapped ocean, with no shoreline, no anchor points, and no bottom. Every object in existence is falling relative to something else, caught in an infinite hierarchy of gravitational attraction that spans from the smallest asteroid to the largest supercluster of galaxies. This lack of an absolute reference frame was the great realization that shattered the foundations of classical physics. For centuries, thinkers imagined the universe was filled with an invisible, unmoving fluid called the luminiferous ether, a universal backdrop that sat perfectly still, allowing light waves to travel through it. If this ether existed, it would mean there was a true, absolute state of rest. It would mean you could build a machine to measure exactly how fast you were moving through the static fabric of creation. But in the late 19th century, brilliant experiments designed to detect the Earth's motion through this ether found absolutely nothing. No matter which way the Earth turned, no matter how fast it orbited, the speed of light remained completely identical in every direction. There was no cosmic wind blowing through the laboratory. The ether didn't exist. There was no static backdrop. The universe, it turned out, was entirely relative. When Albert Einstein took this revelation and ran with it, he unlocked the true relationship between speed, time, and space. He realized that because there is no absolute rest, the laws of physics must look identical to anyone moving at a constant speed, no matter how fast that speed is. If you are inside a windowless spacecraft traveling at 99% the speed of light, your coffee will still pour normally, your heart will beat at its usual rate, and a clock on your wall will tick second by second without a hint of delay. To you, inside your frame of reference, you are perfectly stationary, and it is the rest of the universe that is rushing past your windows at a terrifying velocity. Both perspectives are equally valid, equally true, and equally real. Speed is not a property that you possess all by yourself. It is an expression of how you relate to the objects around you. But this relativity introduces profound, eerie distortions when different moving frames try to look at one another. If an observer on Earth could peer through the window of that high-speed spacecraft, they would see something truly mind-bending. They would see the clock inside the ship ticking incredibly slowly, frozen in a state of suspended animation. They would see the spacecraft itself compressed along its line of motion, flattened like an accordion. Yet, to the astronaut inside, everything remains completely pristine and normal. This is not an optical illusion or a trick played by the lenses of a telescope. It is a fundamental truth about the structure of our universe. Space and time are flexible fabrics that stretch, compress, and warp depending entirely on how fast two observers are moving relative to one another. The faster you move through space, the slower you move through time. They are locked in a cosmic balance, two sides of a single coin called space-time. We do not notice these distortions in our daily lives because the speeds we experience on Earth, even the million-mile-an-hour flight of our galaxy, are still a tiny drop in the bucket compared to the absolute speed limit of the cosmos, the speed of light. Light tears through the vacuum at an astonishing 186,000 miles per second, or roughly 670 million miles per hour. Even our galactic plunge toward the Great Attractor, clocking in at over 1 million miles per hour, is less than 1% of that ultimate cosmic velocity. At these sluggish, subrelativistic speeds, the fabric of time only dilutes by a fraction of a percent, far too small for human clocks or biological senses to ever register. We live in a slow-motion pocket of reality, shielded from the extreme relativistic warping that governs the high-speed fast lanes of the deep universe. But the grandest, most terrifying motion of all doesn't require us to look down at our planet's speed or out at our galaxy's plunge. It requires us to look at the very space separating us from the rest of creation. As we look across the vast abysses that divide the Milky Way from distant galactic communities, we find that the universe is staging a massive disappearing act. Because the expansion of space is accelerating, driven by the mysterious, invisible pressure of dark energy, the cosmos is growing larger every single second. This expansion isn't a physical movement of galaxies tearing through an existing room. it is the creation of new space within the gaps between them. It is as if the cosmic grid itself is being stretched out in all directions at once. On our local scale, gravity acts like a powerful glue. The gravitational bond between the Earth and the Sun keeps our orbit locked tight, preventing the expansion of space from pushing us away from our star. The gravity of the Milky Way keeps our 100 billion companion stars bound together in a beautiful, cohesive spiral, shielding us from the cosmic stretching happening outside our borders. Even our local group of neighboring galaxies, including the massive Andromeda spiral, is held firmly in a gravitational embrace, destined to eventually collide and merge into a single giant galactic city billions of years from now. But once you look past our local neighborhood, past the boundaries of our gravitational fortress, dark energy wins the tug of war. Across the megaparsecs of the deep cosmos, the sheer volume of space is so immense that the cumulative stretching effect becomes an unstoppable force. Galaxies, separated by hundreds of millions of light years, are being pushed apart at speeds that defy imagination. And because Hubble's law dictates that the speed of this recession scales directly with distance, the further out we look, the faster the universe is running away from us. This leads us to a haunting, inescapable conclusion about the ultimate fate of our cosmic journey. There are regions of the universe so incredibly distant that the space between us and them is expanding faster than the speed of light itself. If you were to turn on the most powerful laser beam imaginable and point it toward a galaxy sitting beyond that cosmic horizon, that light would never arrive. Even though the light is racing forward at 670 million miles per hour, the space ahead of it is being manufactured at an even faster rate, stretching the distance faster than the light can cross it. Those distant worlds are permanently, irrevocably cut off from us. They have slipped beyond the edge of our observable universe, vanishing into a dark abyss from which no information, no light, and no communication can ever return. As the eons tick forward, this accelerating expansion will continue to harvest the night sky. Billions of years from now, the space separating our local galactic remnants from the rest of the cosmos will have stretched so violently that every other galaxy in the universe will be carried beyond our horizon. The deep cosmic filaments, the vast walls of galaxies, and the grand structures of the universe will slide one by one into the unseeable darkness. Future astronomers living on our planet, looking up through their telescopes into the deep night, will see absolutely nothing but a cold, empty, featureless void. They will find no evidence of a Big Bang, no sign of distant galaxies, and no clue that they are part of a grander, moving cosmos. They will look out at a completely lonely sky and conclude that their local island of stars is the entirety of creation, completely unaware of the rich, vibrant universe that we can see today. We are incredibly fortunate to live in this specific slice of cosmic time. We are alive during an era where the universe is still close enough, bright enough, and open enough to reveal its secrets to us. We can still look out and read the story of the Big Bang, written in the faint glow of the cosmic microwave background. We can still map our terrifying descent toward the Great Attractor and calculate the grand, sweeping orbits of our sun around the galactic nucleus. We can look at a shooting star and understand it not as an omen, but as a physical touchpoint of our planet's high-speed orbit through the solar system. When you return to your everyday life tomorrow, the illusion of stillness will undoubtedly return. The ground will feel solid beneath your feet, the buildings will look anchored to the bedrock, and the horizon will seem completely stationary. But you will carry the hidden truth with you. You will know that you are a cosmic voyager strapped to a majestic planetary vessel that never sleeps, never slows down, and never stops its relentless journey through the dark. You are spinning faster than sound, orbiting faster than a missile, and hurtling through the deep fabric of space at over 1 million miles per hour. We are all passengers on a magnificent, terrifying flight through an expanding infinity, bound together on a journey toward an unknown future, running through the cosmos at impossible speeds, all while sitting perfectly still in the dark. This terrifying perspective of our cosmic flight forces us to re-examine the very nature of what we call home. We treat the Earth as an unshakable foundation, building our cities, mapping our borders, and anchoring our lives to the solid bedrock. But the bedrock is a passenger just like us. If you could take a step back, breaking free from the gravitational tether of our world, you would see the Earth not as a serene, static blue marble, but as a hypervelocity engine of kinetic energy, slicing through the dark fabric of the solar system with a violence that makes human machinery look like it is standing still. We are riding a giant planetary bullet, and our survival depends entirely on the fact that this bullet travels through a pristine, undisturbed void. To truly understand how precarious this journey is, consider what happens when our planet encounters the tiny remnants of the solar system's formation. Space is not completely empty. It is littered with debris, fragments of pulverized asteroids, icy dust trails left behind by dying comets, and microscopic grains of primordial rock. As the Earth races along its orbit at 66,600 miles per hour, it regularly plows into these drifting clouds of matter. Because of our incredible speed, these encounters are not gentle drifts. They are high-speed, head-on collisions. When a piece of space, dust no larger than a grain of sand, strikes our upper atmosphere, it doesn't just fall to the ground. It hits the thin air molecules at an absolute speed that exceeds any ballistic weapon ever manufactured by humanity. The sheer kinetic energy of the collision compresses the air ahead of the particle so violently that the gas molecules ionize and glow, reaching temperatures of thousands of degrees in a fraction of a second. This is the origin of a shooting star. When you look up at the night sky and see a brilliant, fleeting streak of light, you are not watching a star fall. You are witnessing a direct visual proof of Earth's terrifying orbital speed. You are watching a planetary windshield smash through space debris at speeds that instantly vaporize solid rock. The atmosphere acts as a hypervelocity shield, absorbing the kinetic shockwaves of our endless sprint through the solar system, turning potential devastation into a beautiful, silent light show for the observers below. Yet, as violent as these atmospheric impacts are, they are merely the local friction of our immediate neighborhood. If we zoom out to the very edge of the sun's domain, we find a much larger, grander frontier, where our entire solar system asserts its presence against the rest of the galaxy. The sun is not just an unmoving ball of light. It is a dynamic, magnetic powerhouse that constantly exhales a roaring stream of charged particles known as the solar wind. This wind blows outward in all directions, creating a massive, protective bubble that encapsulates all the planets, asteroids, and comets. We call this bubble the heliosphere. As the sun screams through the Milky Way at nearly 500,000 miles per hour, it drags this massive heliospheric bubble along with it. The heliosphere doesn't travel through an absolute vacuum. It is actively plowing through the interstellar medium, the cold, thin gas and dust that fills the spaces between the stars. Just like the bow of a massive ship cutting through the ocean waves, the high-speed plunge of our solar system carves a giant V-shaped wake through the galactic gas. For decades, scientists theorized that this 500,000 mile-an-hour journey created a violent bow shock ahead of us, a point where the interstellar medium is suddenly compressed into a turbulent wall of plasma. While recent data from our deep space probes suggests the transition might be a smooth, glowing bow wave rather than a sharp shock wave, the physical reality remains unchanged. Our solar system is actively fighting its way through the galaxy, a cosmic projectile ripping open a tunnel through interstellar space, leaving a long, turbulent trail of solar particles in its wake. The mechanics of this galactic journey become even more dizzying when you look at the geometry of our flight. The Milky Way is a giant, spinning disk of stars, gas, and dark matter, organized into majestic spiral arms. It would be easy to imagine that our solar system orbits the center of this disk, like a flat record player needle, riding smoothly along the galactic plane. But nature rarely prefers simple symmetry. The plane of our solar system, the flat tabletop where Earth and the other planets orbit the sun, is tilted at a sharp, awkward angle of about 60 degrees relative to the disk of the galaxy. We are not upright. We are flying through the galaxy sideways, tilted like a spinning coin thrown across a room. Furthermore, our path around the galactic core is not a smooth, flat circle. As the Sun moves forward at 490,000 miles per hour, it undergoes a slow, rhythmic vertical oscillation, bobbing up and down through the dense sheet of stars that makes up the galactic equator. The midplane of the galaxy contains a high concentration of mass, which exerts a powerful gravitational pull. As our solar system travels forward, the gravity of this dense galactic sheet pulls the Sun toward it. The Sun plunges down through the plane, but because of its immense forward momentum, it overshoots the center, climbing high above the northern side of the galactic disk. Eventually, the collective gravity of the plane acts like a giant elastic band, slowing the Sun's ascent, stopping it, and pulling it back down. The Sun then plunges back through the plane to the southern side, overshoots again, and repeats the process. This vertical cosmic bobbing takes tens of millions of years to complete a single cycle. Right now, you are sitting on a planet that is spinning on a tilted axis, orbiting a star on a tilted plane, while that star corkscrews its way up and down through the crowded disk of a massive, rotating galaxy. It is a roller coaster of unimaginable proportions, driven by the invisible hands of orbital mechanics, operating on scales of time and space that reduce the entire history of human civilization to a microscopic fraction of a single galactic wobble. When you stack all these layers together, the 1,000-mile-an-hour spin, the 66,000-mile-an-hour orbit, the 500,000-mile-an-hour stellar sprint, and the 1.5-mile-an-hour galactic plunge, you begin to see why the classic concept of a fixed point in space is completely meaningless. In our daily lives, we rely entirely on the security of fixed points. We reference our location by a street corner, a building, a mountain range, or a specific set of latitude and longitude coordinates. But the universe does not recognize our geography. If you were to step off the surface of the Earth right now, teleporting into the deep vacuum, while leaving yourself fixed to the exact spatial coordinates you occupied just 5 minutes ago, you would instantly find yourself stranded in a cold, featureless void, thousands of miles away from the planet. In those 5 minutes, the Earth would have spun out from beneath your feet, surged tens of thousands of miles ahead in its orbit around the Sun, and been dragged into an entirely new sector of the galaxy by the Sun's relentless flight toward the stars. Space has no memory of where we were. It is a vast, unmapped ocean with no shoreline, no anchor points, and no bottom. Every object in existence is falling relative to something else, caught in an infinite hierarchy of gravitational attraction that spans from the smallest speck of dust to the largest supercluster of galaxies. This profound realization that there is no such thing as an absolute position or an absolute state of rest was the great philosophical and scientific breakthrough that shattered the foundations of classical physics. For centuries, the greatest minds in science imagined that the universe was filled with an invisible, unmoving, frictionless fluid called the luminiferous ether. This ether was thought to be the ultimate cosmic backdrop, a universal fabric that sat perfectly still, providing a medium through which light waves could travel. If this ether existed, it would mean there was a true, objective standard of stillness. It would mean that somewhere in the universe there was a laboratory that was truly at rest, and you could build a machine to measure exactly how fast you were moving relative to the stationary fabric of creation. But in the late 19th century, a series of brilliant, incredibly precise experiments designed to detect the Earth's motion through this ether found absolutely nothing. Scientists measured the speed of light in the direction of Earth's orbital flight, and then measured it perpendicular to our flight, expecting to see a difference caused by the cosmic wind of our movement. Instead, the speed of light remained completely identical, down to the last decimal point, in every direction, at every time of day, and during every season of the year. There was no cosmic wind blowing through the laboratory. The ether didn't exist. There was no static backdrop, no universal floor, and no cosmic grid. The universe, it turned out, was entirely fundamentally relative. When Albert Einstein took this revelation and used it to construct his theory of relativity, he unlocked the true, terrifying relationship between speed, time, and space. He realized that, because there is no absolute rest, the laws of physics must look exactly the same to anyone moving at a constant speed, no matter how fast that speed might be. If you were inside a completely sealed, windowless spacecraft, traveling through the void at 99% the speed of light, your experience of reality will be completely indistinguishable from sitting in your living room on Earth. Your coffee will pour normally, your heart will beat at its usual steady rhythm, and a clock ticking on your wall will mark the passage of time second by second without a hint of delay. To you, inside your frame of reference, you are perfectly stationary, and it is the rest of the universe that is rushing past your windows at a mind-bending velocity. Both perspectives are equally valid, equally true, and equally real. Speed is not a permanent property that you possess all by yourself. It is an expression of how you relate to the objects around you. But this relativity introduces profound, eerie distortions when different moving frames try to look at one another. If an observer standing on Earth could look through a telescope and peer through the window of that high-speed spacecraft, they would see something that challenges our very understanding of logic. They would see the clock inside the ship ticking incredibly slowly, as if the crew were frozen in a state of suspended animation. They would see the spacecraft itself compressed along its line of motion, flattened like an accordion. Yet, to the astronaut inside the ship, everything remains completely pristine, normal, and unaltered. This is not an optical illusion, a trick of the light, or a mechanical flaw in the telescope. It is a fundamental truth about the structure of our universe. Space and time are not rigid, unyielding constants. They are flexible fabrics that stretch, compress, and warp, depending entirely on how fast two observers are moving relative to one another. The faster you move through space, the slower you move through time. They are locked in a cosmic balance, two dimensions woven together into a single dynamic tapestry called space-time. We do not notice these bizarre distortions in our daily lives because the speeds we experience on Earth, even the million-mile-an-hour flight of our galaxy, are still a tiny drop in the bucket compared to the absolute speed limit of the universe, the speed of light. Light tears through the vacuum at an astonishing 186,000 miles per second, which translates to roughly 670 million miles per hour. Even our galactic plunge toward the Great Attractor, clocking in at over 1 million miles per hour, is less than 1% of that ultimate cosmic velocity limit. At these sluggish, sub-relativistic speeds, the fabric of time only dilutes by a fraction of a percent, far too small for human clocks or biological senses to ever register. We live our lives in a slow-motion pocket of reality, shielded by our low velocities from the extreme relativistic warping that governs the high-speed fast lanes of the deep universe. But the grandest, most terrifying motion of all doesn't require us to look down at our planet's spin or out at our galaxy's plunge. It requires us to look at the very space separating us from the rest of creation. As we look across the vast abysses that divide the Milky Way from distant galactic communities, we find that the universe is staging a massive disappearing act. Because the expansion of space is accelerating, driven by the mysterious invisible pressure of dark energy, the cosmos is growing larger every single second. This expansion isn't a physical movement of galaxies tearing through an existing room. It is the creation of new space within the gaps between them. It is as if the cosmic grid itself is being stretched out in all directions at once. On our local scale, gravity acts like a powerful glue. The gravitational bond between the Earth and the Sun keeps our orbit locked tight, preventing the expansion of space from pushing us away from our star. The gravity of the Milky Way keeps our 100 billion companion stars bound together in a beautiful, cohesive spiral, shielding us from the cosmic stretching happening outside our borders. Even our local group of neighboring galaxies, including the massive Andromeda spiral, is held firmly in a gravitational embrace, destined to eventually collide and merge into a single giant galactic city billions of years from now. But once you look past our local neighborhood, past the boundaries of our gravitational fortress, dark energy wins the tug of war. Across the megaparsecs of the deep cosmos, the sheer volume of space is so immense that the cumulative stretching effect becomes an unstoppable force. Galaxies separated by hundreds of millions of light-years are being pushed apart at speeds that defy imagination. And because Hubble's law dictates that the speed of this recession scales directly with distance, the further out we look, the faster the universe is running away from us. This leads us to a haunting, inescapable conclusion about the ultimate fate of our cosmic journey. There are regions of the universe so incredibly distant that the space between us and them is expanding faster than the speed of light itself. If you were to turn on the most powerful laser beam imaginable and point it toward a galaxy sitting beyond that cosmic horizon, that light would never arrive. Even though the light is racing forward at 670 million miles per hour, the space ahead of it is being manufactured at an even faster rate, stretching the distance faster than the light can cross it. Those distant worlds are permanently, irrevocably cut off from us. They have slipped beyond the edge of our observable universe, vanishing into a dark abyss from which no information, no light, and no communication can ever return. As the eons tick forward, this accelerating expansion will continue to harvest the night sky. Billions of years from now, the space separating our local galactic remnants from the rest of the cosmos will have stretched so violently that every other galaxy in the universe will be carried beyond our horizon. The deep cosmic filaments, the vast walls of galaxies, and the grand structures of the universe will slide one by one into the unseeable darkness. Future astronomers living on our planet, looking up through their telescopes into the deep night, will see absolutely nothing but a cold, empty, featureless void. They will find no evidence of a Big Bang, no sign of distant galaxies, and no clue that they are part of a grander, moving cosmos. They will look out at a completely lonely sky and conclude that their local island of stars is the entirety of creation, completely unaware of the rich, vibrant universe that we can see today. We are incredibly fortunate to live in this specific slice of cosmic time. We are alive during an era where the universe is still close enough, bright enough, and open enough to reveal its secrets to us. We can still look out and read the story of the Big Bang, written in the faint glow of the cosmic microwave background. We can still map our terrifying descent toward the Great Attractor and calculate the grand, sweeping orbits of our sun around the galactic nucleus.